In this video, I will discuss trade-offs in disinfection byproduct management. During the treatment process, operators must balance the risks of incomplete disinfection and DBP formation. If disinfection is incomplete, there may be harmful pathogens in the finished water, threatening human health. However, chlorine-containing compounds used for disinfection can also react with DBP precursors to form cancer-causing disinfection byproducts, also threatening human health. Therefore, an operator has two goals: ensure disinfection and avoid DBP formation. To meet goal number one, chlorine should be added until all harmful pathogens are destroyed. In addition, enough chlorine should be added to produce some free residual chlorine, which keeps the water free of pathogens in the distribution system. To better understand this concept, we are going to introduce some key terminology and calculations that you will need to know to operate a drinking water treatment plant. First, the amount of chlorine added is the chlorine dose, while the chlorine used up by pathogens and other substances in the water is the chlorine demand. The chlorine left over from the dose after demand is satisfied is the chlorine residual. This brings us to our first calculation, the dose calculation. The chlorine dose in milligrams per liter is equal to the demand plus the residual, which are also both in milligrams per liter. So for example, if you needed to know what chlorine dosage should be applied to raw water with a demand of 0.5 milligrams per liter and an intended residual of 1.1 milligrams per liter, you would add the demand and the residual to find that your dosage should be 1.6 milligrams per liter of chlorine. Once you know the required dose, you might also need to know how much chlorine chemical to feed per day to achieve that dosage, given the flow in the plant you are operating. To find out how much chemical to feed in pounds per day, you would use the pounds formula. It says that the chlorine chemical in pounds per day is equal to the chlorine dose times the flow in the plant times the constant of 8.34 pounds per gallon, which is the number of pounds of water per gallon. So for example, if you needed to know the chlorine feed rate setting in pounds per day, given a plant flow of 0.8 million gallons per day and a required chlorine dose of 1.6 milligrams per liter, you would multiply the dose by the flow and then by the constant of 8.34 pounds per gallon to determine that you need to feed 10.7 pounds per day of chlorine. The final concept we will cover related to ensuring disinfection is breakpoint chlorination. Breakpoint chlorination is a useful framework that helps operators know how much chlorine is needed for disinfection and production of free residual chlorine. To ensure complete disinfection, chlorine should be added until the breakpoint on the figure is reached. Let's walk step by step through this figure. On the x-axis, we have the amount of chlorine added during treatment, while on the y-axis, we have the amount of chlorine residual left after disinfection occurs. In the first zone on the figure, when only a little chlorine is added to the water, that chlorine reacts with reducing agents in the water, such as iron, manganese, and nitrite, and there is no residual left over. In zone 2, as more chlorine is added, the chlorine reacts with ammonia and organic matter to form chloramines and chlororganic compounds, combined residual chlorine. The primary reaction in this zone is the reaction of chlorine and ammonia, resulting in combined residual of primarily monochloramine. In zone 3, the addition of more chlorine leads to destruction of the chlororganic compounds and monochloramine from zone 2, leading to decreased combined residual. This zone is also where formation of dichloramines and trichloramines can occur, which can lead to taste and odor problems in drinking water, until the breakpoint is reached. At the dip between zones 3 and 4, known as the breakpoint, these dichloramines and trichloramines decompose, and free chlorine residual persists and then begins to accumulate in zone 4. This is the point at which we achieve complete disinfection. After the breakpoint, chlorine builds up in the water as free chlorine residual. Having some free available residual is good to ensure disinfected water throughout the distribution system. However, too much residual can lead to disinfection byproduct formation in the distribution system, particularly if there are high levels of organic compounds present in the distribution system. As an operator, it is important to know whether you have reached breakpoint chlorination. You can determine whether the breakpoint has been reached by comparing the values of the actual versus expected increases in the chlorine residual. Expected increase in residual is the amount of residual we expect, given the addition of a specific amount of chlorine and assuming we have already reached the breakpoint. Actual increase in residual is the amount of residual we actually get, given the addition of a specific amount of chlorine. If the actual residual is less than the expected residual, we have not reached the breakpoint. On the next slides, we will walk through the 3 steps of this calculation and work an example problem. The first step in determining whether you have reached breakpoint chlorination is to calculate the expected increase in residual. The expected increase in the residual is equal to the increase in chlorine added during the treatment process in pounds per day, divided by the flow in million gallons per day, times the number of pounds of water per gallon. The second step is to calculate the actual increase in residual that you observe when you increase the amount of chlorine. To do this, you subtract the old residual before more chlorine was added from the new residual after more chlorine was added. The new and old residuals will be determined by laboratory testing conducted at the treatment plant. The final step in determining if you have reached breakpoint chlorination is to compare the actual and expected increases in residual. If the actual residual is less than the expected residual, breakpoint chlorination was not reached. If the actual residual is greater than or equal to the expected residual, breakpoint was reached. Now let's work an example problem. A chlorinator setting of 15 pounds of chlorine per day results in a chlorine residual of 0.3 milligrams per liter. The chlorinator setting is increased to 20 pounds per day. The chlorine residual increases to 0.45 milligrams per liter at this new dosage rate. The average flow being treated is 1.4 million gallons per day. On the basis of these data, is the water being chlorinated past the breakpoint? First, we calculate the expected residual, which is the increase in chlorine of 5 pounds per day divided by the flow of 1.4 million gallons per day times the number of pounds of water per gallon, 8.34 pounds per gallon. This gives us an expected residual of 0.43 milligrams per liter of chlorine. Next, we calculate the actual residual, which is the old residual, 0.3 milligrams per liter, subtracted from the new residual after more chlorine was added, which is 0.45 milligrams per liter. This gives us an actual residual of 0.15 milligrams per liter. Finally, we compare the actual and expected residual. We see that the actual residual of 0.15 milligrams per liter is less than the expected residual of 0.43 milligrams per liter, and so we conclude the water is not being treated past the breakpoint. All of this information regarding breakpoint chlorination and residuals begs the question, how much residual should you aim for? Chlorine feed systems for secondary disinfection should achieve a minimum chlorine residual at the entry point of 0.2 milligrams per liter for more than 4 hours. However, the maximum allowed residuals is 4.0 milligrams per liter because of the risk of formation of disinfection byproducts, which we will discuss next. The second goal for operators, in addition to ensuring disinfection, is to avoid DBP formation. The best approach to avoiding DBP formation is to remove DBP precursors prior to disinfection. To do this, operators have several options. They can increase the coagulation and clarification time or add more coagulant. They can activate carbon filters that absorb organic matter or pass water through a membrane that filters out DBP precursors. Because excessive free chlorine residual can lead to formation of DBPs in the distribution system, the EPA and VDH have enacted MRDLs, or maximum residual detection limits. The table on the slide shows the MRDLs for 3 chlorine compounds that are commonly used for disinfection. The free chlorine residual in treated water must remain below the MRDLs listed in the table. In summary, here is a high-level strategy for operators to balance the goals of ensuring disinfection and avoiding DBP formation. First, operators must ensure that water is chlorinated to breakpoint. Second, operators may use additional treatment steps as needed, such as increased coagulation, activated carbon filters, or membrane technology to remove DBP precursors prior to disinfection. This helps avoid DBP formation in the treatment plant. Finally, operators must keep treated water under the EPA and VDH MRDL of 4.0 milligrams per liter for free chlorine residual. This helps avoid DBP formation in the distribution system. This is the end of the video. Thanks for your attention.